Hello students, welcome you all back to another session of Econometric Methods course. Last class we saw how estimators are derived using different principles for a regression model. Today we are going to see the characteristics of estimators with different parameters defined. In the last session we also see for the different OLS assumptions, the estimators derived from different principles coincide or give the same results. Therefore, today with the OLS assumptions in place, we are going to derive the characteristics of the estimators derived from the OLS assumptions. Now let us see how estimators are evaluated for their properties. Let us see. Evaluation of different estimators are based on performance of them on repeated samples. Usually the data we got from the population is supposed to be generated on a data generating process. Let us assume the data generating process, that is usually the population regression function y equal to alpha plus beta x plus u. This model generates sample relating y and x. Let us assume the population as x1 y1 x2 y2 up to xn yn, that is the n is the size of the population. From this population, the using random method, we may select n samples, small n samples. Let that sample be x1 y1 x2 y2 etc. x small n y small n. So from n population size, we may take the sample of small n size with these possibilities, capital N, Cn possibilities are there. Let us take those NCN samples as here, the sample 1 x1 y1 x2 y2 up to x small n yn. This is the first sample. We may have a second sample. This sample may go up to NCN cases. This is the sample of last possibility. For each sample, we may calculate the estimate using our OLS estimators. We have estimator for alpha and we have estimator for beta. From corresponding to the first sample, we may get as alpha hat 1, alpha hat 2. Similarly, for the second sample, we may get the second estimate alpha hat 2, alpha hat 3. Like that, we may have NCN estimates. Using these estimates, we may form sampling distribution. Let the sampling distribution be f of alpha hat beta hat. This sampling distribution may have a characteristic defined by its mean and its variance. The mean of the estimator beta hat may be defined as mean or expectation of beta hat, and variance or variance of beta hat. Similarly, the same can be defined for alpha hat also. Let us derive the mean of beta hat or expectation of beta hat. Let us take beta hat is equal to sigma xi yi divided by sigma xi square. This is the OLS estimator we derived. Here xi is equal to capital Xi minus x bar, small yi is equal to capital Yi minus y bar, as these small xi's and small yi's are the deviations of the original observation from its means. Now, for the arithmetic convenience, let us assume this xi divided by sigma xi square as wi. So we may rewrite the original beta hat as this one, and we may further write this as small wi yi, where small wi is equal to small xi divided by sigma small xi square. Here one, we will just derive the characteristics of small wi. Now let us define the characteristics of wi first. Here sigma wi is equal to sigma of xi divided by sigma xi square, because xi we know the value of wi, so I am just substituting that value, and this is equal to sigma xi divided by sigma xi square. Here interestingly, this sigma wi is equal to 0, because this is just the summation of observations from its deviation from mean, actually deviation measure of the observed xi. So sum of it is equal to 0. So that is equal to numerator 0 divided by sigma xi square, that is equal to 0 now. So sigma wi is equal to 0. Similarly, sigma wi square is equal to sigma of xi divided by sigma xi square whole square. So this is equal to sigma xi square divided by sigma xi square whole square. If you cut it, then we will get 1 by sigma xi square. So sigma wi square is equal to 1 by sigma xi square. Similarly, we may derive the value for sigma wi xi as well. Sigma wi xi is equal to sigma of xi divided by sigma xi square, that is w, and xi. So if we multiply these two xi's, we get sigma xi square divided by sigma xi square. So the end value is 1. So sigma xi wi is equal to 1. Now let us take the value of sigma wi and capital Xi. Capital Xi is nothing but, we know the equation between the relationship between small xi and capital Xi. So capital Xi is nothing but small xi plus x bar. So we are substituting this value for capital Xi. So we get wi small xi plus x bar. Now we are multiplying this wi and xi and wi and x bar. We may reduce this expression as sigma wi xi plus x bar sigma wi. So here sigma wi xi is equal to 1 and sigma wi is 0, and so substituting these values we get 1 plus x bar into 0, that is 1 into 0, 1 plus 0, that is equal to 1. So we get the value sigma wi capital Xi is equal to 1, very similar to sigma wi small xi. Now after this, the characterization of wi, now we'll see the actual beta hat. beta hat is equal to sigma wi small yi. This may again this small yi may be written as capital Yi minus y bar. So we may get the equation expanded like this: sigma wi capital Yi minus y bar to small wi. We all know the value of this small wi is equal to 0, and so sigma wi small yi is equal to sigma wi capital Yi. Now we will substitute the value for yi, capital Yi, that is equal to alpha plus beta xi plus ui from the original data generating model. So this is equal to sigma wi into that expression. We may multiply this wi inside and we can take the sigma. So that will reduce this expression into alpha sigma wi plus beta into sigma wi capital Xi plus sigma wi capital Ui. So now this sigma wi is equal to 0 and this expression is equal to 1, and so we get alpha into 0 plus beta into 1 plus sigma wi ui. Actually this comes from this one, beta plus sigma wi ui. Let us take expectations both sides. We get expectation of beta hat is equal to expectation of beta plus sigma wi ui. Here we already know beta and wi are non-stochastic. So the expectation is applicable only to the stochastic term ui. So this is reduced to beta hat plus sigma wi expectation of ui. This is nothing but because this expectation of ui is equal to 0 for every I is the OLS assumption. Based on the OLS assumption, we get beta plus sigma wi into 0 for every I. So that reduces this equation to expectation of beta hat is equal to beta. This is an important result we derive. That means the mean of beta hat is beta under OLS assumptions. So the average or mean of beta hat in the sampling distribution is beta. Now let us see the mean or the expectation of alpha hat. Alpha hat we already know, y bar minus beta hat x bar. Let us expand it a little bit. Y bar is nothing but sigma capital Yi by n, that is 1 by n into sigma Yi. Similarly, beta hat is nothing but sigma Wi Yi. Now let us reduce this into this form 1 by n. Actually we may take Yi commonly outside and we get this other terms like this: 1 by n minus sigma 1 by n minus Wi x bar into Yi. So if you multiply Yi, we get this one, Yi by n minus x bar Wi Yi. If you substitute the value for Yi, we get 1 by n sigma alpha plus beta xi plus ui minus x bar outside sigma Wi into Yi inside, that is alpha plus beta xi plus ui. We will reduce to this equation into two things. One is we are multiplying this Wi inside this expression and taking sigma out. So we are reducing this equation into this one. So this is equal to, we are getting this sigma inside. So 1 by n, this is now n times the alpha is added. So n alpha plus beta into sigma xi by n plus sigma ui by n. So you get this one, minus taking x bar outside, inside you are multiplying this wi, we get sigma alpha wi plus beta wi xi plus wi ui. Now we are again taking this sigma inside, multiplying this x bar into the expression. So this is reduced to this alpha, the 1 by n, n cancelled. So alpha plus this sigma xi by n is x bar. So beta x bar plus sigma ui by n, you get minus, and within this expression you get x bar alpha into sigma wi. This expression is by sigma wi. The second expression, this this beta is taken outside and already one x bar is there. So x bar beta into inside sigma wi capital Xi plus x bar is there outside, and you get sigma wi ui inside. Now this can be further reduced, this expression carried, and within that this small wi is equal to 0, we already know, and this sigma wi capital Xi is equal to 1, and we are substituting this value, we get x bar alpha into 0 plus x bar beta into 1 plus x bar sigma wi ui. So we are carrying this minus sign inside, we get alpha plus beta x bar plus sigma ui by n minus, multiplying this minus into this, we get minus x bar beta minus x bar sigma wi ui. So this is what you get, and so now alpha plus sigma is carried outside, so you get 1 by n minus x bar wi whole to ui. So this is the expression we got at last. Taking expectations both sides, get expectation of alpha hat is equal to expectation of alpha plus 1 by n sigma ui minus x bar into sigma wi ui. We all know this expression only ui is stochastic. Now taking expectations inside, we get alpha plus 1 by n sigma expectation of ui minus x bar sigma wi expectation of ui. So we all know, already know, we know by OLS assumption that expectation of ui is 0 for every I. So we get further reduction as alpha plus 1 by n into 0 for all the expectation of ui is 0 and the sum of it is 0 minus x bar into sigma wi into 0 because expectation of ui is 0. So we get alpha plus 0 because these two terms are 0, and ultimately expectation of alpha hat is equal to alpha. So we can infer that the mean or expectation of alpha hat is alpha, very similar to the estimator of beta hat, where expectation of beta hat is equal to beta. In today's class, we saw the characteristics of alpha hat and beta hat in the stochastic distribution of repeated samples. We saw the mean or expectation of beta hat is equal to beta, and the expectation of alpha hat is equal to alpha. This is an important characteristic of the OLS estimators. This is very important to define the properties of OLS estimators. In the next classes, we will see some more characteristics. For example, the variance of alpha hat and beta hat and the covariance between alpha hat and beta hat. With those characteristics, we would summarize the properties of the OLS estimators. Thank you.